Chapter 3, Part 2, Structure and Relative Acidity. The relationship between structure and acidity can be really helpful. What do you do if you're looking at a reaction and you have no idea what the pKa's of each of the compounds are, but you're being asked to identify which direction the equilibrium lies? Well, you can use your context clues. If you understand how structure and acidity are related, you can solve those problems. So when pK values are not known, the structure of a molecule can give us a good estimate of the relative acidity, which is really all that matters. The factors that affect acidity include electronegativity, hybridization, resonance, and the inductive effect. Acidity is directly related to the stability of the conjugate base. The more stable the conjugate base, the more acidic the acid, which is another way of saying that if the conjugate base is happy without a proton, it's not going to take a proton back. So its conjugate acid would be very, very acidic and very happy to donate a proton. Our first factor is electronegativity, and I think this is also one of our more misleading factors because we remember very well from our periodic trends that electronegativity increases from the bottom left to the top right. So let's look at our trends here. As we move from left to right across a period of the periodic table, we see increasing acidity, which makes a lot of sense because the bond between hydrogen and carbon is barely polarized, which means there's not a real reason for this bond between hydrogen and carbon to break. But by the time you get to hydrofluoric acid, this bond is very polar. The hydrogen has a pretty solid partial positive and the fluorine has a partial negative. They are moving towards becoming practically an ionic species. So it makes sense that hydrofluoric acid would be more acidic. Notice also that we're just swapping out the atom that the hydrogen is attached to. So we go from carbon to nitrogen and our pK drops 10 points. From nitrogen to oxygen, we drop 20 points. And then going down to hydrogen and fluorine, we drop another like 12 points. So these changes in acidity are significant. Another thing to pay attention to is that all of these compounds that we're looking at only have two elements. So we are looking at hydrogen directly attached to carbon, and there's nothing else on this molecule. Hydrogen directly attached to nitrogen, and nothing else on the molecule. So this only applies to compounds that contain only two elements. Now, what about this is misleading? Because so far, we're following our trend. Well, acidity increases down a group as atomic radius increases. And that's the part that's confusing for people. Now, the way that I keep this straight in my head is that I remember that hydrofluoric acid is a weak acid and hydriodic is a strong acid. So in order for that to work, acidity must be increasing down the group. Now, let's talk about why. So, acidity is based on the fact that the conjugate base will be stable without the proton. And the more stable the conjugate base, the more acidic the acid. So let's look at fluorine. Fluorine is a tiny, tight ball of negative charge, essentially. It has a much smaller electron cloud than, let's say, iodine. So, fluorine, being this tiny, tight, negative ball of electrons, essentially, is going to be very attracted to its positive proton. And the bond between them is going to be kind of difficult to break. But by the time you get down to massive iodine, the valence electrons and the charge, the negative charge of the electrons, is being spread out across a much larger surface area. So that positively charged proton is having a much harder time creating a strong bond to it. So the bond between iodine and hydrogen is much weaker, which means the proton is going to be easier to free and easier to take away. Another thing to consider is that once hydrogen is pulled away from hydroiodic acid, you're going to be left with iodide minus and a proton. And if you look at hydrofluoric acid, you'd be stuck with F minus and a proton. Now remember that both of these halogens have the same 8 electrons around them at this point, which is a full shell, but they're also carrying a negative charge. And iodine gets to spread that negative charge across its massive electron cloud, while fluorine has to have that negative charge in its tiny electron cloud. With the iodide anion, that negative charge is much more dispersed, whereas with fluorine, it's very concentrated. That's never going to be stable. Think back to the concept of resonance. If you are able to delocalize a charge, that's going to be a stabilizing factor. Okay, let's look at hybridization. How does the hybridization of an atom affect the acidity? Well, the s orbital electrons are lower energy than p orbitals, and this is because they are closer to the nucleus. Remember that the nucleus is positively charged, the electrons are negatively charged. So the closer they are together, the more stable that's going to be. So the more S character that something has, the more stable the anion and the more acidic it can be. So let's take a look at our alkyne. This carbon is sp hybridized. It is 50% S character. When we look at ethene, this carbon is sp2 hybridized. It is 30% S character. And then by the time we get to ethane, we are sp3 hybridized and only 25% S character. So acidity is increasing this way because the alkyne has much more S character, which means that when it's deprotonated and the alkynide anion is formed, that negative charge is held in a lower energy orbital, which is favorable. But if we look at the relative basicity, remember that the trends between acidity and basicity are opposite. So a deprotonated alkyne is honestly a pretty good base because the pKa of this is 25. So it's a better base than hydroxide, but it's not going to be as good a base as a deprotonated alkane. The pKa of this proton is closer to 50. So we had to have one really, really strong base in order to even make this at all. So if you get this compound anywhere near something that has an even slightly acidic proton, it's going to steal it and go back to being an alkane. Okay, so let's take a look at resonance. How does resonance affect acidity? Well, again, we talked about how the more stable the conjugate base is, the more acidic the compound. And we know that resonance is stabilizing. So what we're looking for here is if I deprotonate this compound, is the conjugate base resonance stabilized or not? So in this first reaction between water and acetic acid, we can see the protons of water, or electrons of water, picking up the proton from acetic acid and putting the electrons onto the oxygen. This gives us the acetate anion. Now the acetate anion is resonance stabilized. It has a resonance form where it can take this electron density, or this lone pair, and create a pi bond. And this pi bond can get pushed up onto the oxygen, giving us a resonance form, where the negative charge is on that top oxygen, and the oxygen on the bottom right now has a double bond. So these resonance forms are stabilizing because that negative charge that we created by deprotonating is destabilized across the two oxygens. Now, if we look at the similar reaction below, we have ethanol and water. And ethanol was chosen for this example because ethanol and acetic acid have the same number of carbons. So all that's missing from ethanol is the carbonyl. So if we take water and try to deprotonate ethanol, we're going to end up with ethoxide as the conjugate base. And ethoxide does not have any resonance forms, and therefore there is nothing to help stabilize it. That doesn't mean that ethoxide is, completely unstable and never ever going to form. You would just need a much stronger base to make that occur. Now, we can also look at the relative pKa's and try to decide which directions each of these equilibria would lie. So the pKa of acetic acid is 4.76. The pKa of this proton in hydronium is negative 1.74. So the reactants are going to be favored because they have the weaker acid. And if we look at the reaction between ethanol and water, ethanol has a pKa of 15.9. And again, hydronium has a pKa of negative 1.74. So again, we're going to favor the reactants. But these are not the same equilibrium. The difference between the pKa of acetic acid and hydronium is much less significant than the difference of pKa between ethanol and hydronium. So if we were comparing these equilibriums, there is much more product being formed from the top reaction than there ever will be from the bottom reaction. Another factor that has a huge effect on acidity is the inductive effect. And the inductive effect is the one that you're probably going to apply the most often. Induction is when electronegative atoms draw electron density towards themselves, weakening the bond of the proton to the conjugate base. So let's look at acetic acid again, for example, versus ethanol. Acetic acid, again, has a pK of about 4.76, whereas ethanol has a pK of around 15.9. Acetic acid is a much stronger acid, and we already said that acetic acid has resonance going for it, but it also has something else. It has the inductive effect. So, if you're looking at ethanol, the electron density is going towards the oxygen. And so there's a pretty significant partial negative on the oxygen, pretty significant partial positive on the hydrogen. But if you look at acetic acid, the electron density is getting pulled towards this oxygen and towards this oxygen. And so since we have two oxygens that are also in resonance with each other, which shows that we can pull the electron density from this oxygen that has the proton onto this oxygen that does not currently have a proton, shows us that this bond between the oxygen and hydrogen is much, much weaker than the bond between the oxygen and hydrogen in ethanol. And we can actually see this if we draw out the resonance form of acetic acid just as it is. So remembering the arrow pushing that I just drew a second ago, we can draw kind of a crummy resonance form. And you'll see why it's crummy in a second. Because we've created a positive charge on the oxygen and a negative charge on the other oxygen. We've created a separation of charge. And also now the acidic proton, which we know is partially positive, is attached to an atom that has a positive charge. And remember, all resonance forms are contributing in some way. So in some form, this oxygen has maybe potentially a partial positive, or at least electron density is getting pulled towards the other oxygen as well. So the electron density on our oxygen in acetic acid is not as great as the electron density on the oxygen of ethanol. And overall, that's going to weaken the bond between oxygen and hydrogen, meaning it's going to be much easier to take this hydrogen and run. The inductive effect also has some pretty interesting effects when it comes to electronegative substituents. So to illustrate this, we're going to look at acetic acid, fluoroacetic acid, difluoroacetic acid and trifluoroacetic acid. We already discussed the effect that the inductive effect has on acetic acid itself. The pKa of this proton equals about 4.76. And I think we can all agree that the overall motion of the electrons is towards the oxygens, right? And you also have one kind of this way. So overall, the electron density is kind of focused here, which means the proton is going to be attracted to that oxygen. But when you add on one fluorine, remembering that fluorine is the most electronegative atom, we start to have an effect and chip away at this dipole. So while the overall effect is probably still going towards the oxygens, we also have this fluorine that's pulling some electron density away from this oxygen-hydrogen bond. And that decreases the pKa to 2.59, making it slightly more acidic. Now, if you add on one more fluorine, fluorine is more electronegative than oxygen. I don't know how I switched to green all of a sudden. Whoops. And that's going to start flipping our dipole. So the pKa of this proton is 1.34. By the time you've added on 3 fluorines, you have reversed that dipole entirely. The electron density is getting really focused on this end of the molecule, and this bond is severely weakened. So the pKa of this proton is 0.23. So there are 2 reasons that this matters. One is the dispersal of charge stabilizes the conjugate base. By having electronegative atoms on the other side of the molecule, we are pulling electron density away from the negative oxygen that would be created in the deprotonation. So looking at trifluoroacetic acid, if we were to deprotonate it, we would end up with trifluoroacetic acetate. And that negative charge is stabilized through resonance, but also through the pulling of electron density by the 3 fluorines. And another reason is that the withdrawal of electron density from the OH bond weakens the OH bond. Okay, let's take a look at phenols as acids. So this is cyclohexanol. The pKa of the proton on cyclohexanol is roughly 18. This is phenol. The pKa on phenol is around 9.89. So in this case, why do 2 compounds that have the same number of carbons and a very similar structure have very different pKas? And the reason is that the benzene ring in phenol is electron withdrawing. So both the phenol and the phenoxide have several resonance forms. And this is something that would be really good to practice actually if you're still struggling with resonance forms at this point. Deprotonate phenol to get phenoxide. And practice moving this charge around because there are several resonance forms. I'll go ahead and draw one out. You can take one of the electron pairs and create a double bond. Take one of the electron pairs in the pi bonds in the benzene ring and move it to put the electrons on the neighboring carbon. This gives you one of the many, many resonance forms of phenoxide. And having those resonance forms is going to stabilize the conjugate base and therefore make the acid more acidic. Whereas the cyclohexanol does not have any resonance forms. Once you deprotonate it, it's just a deprotonated cyclohexanol. It's just an alkoxide. There's no resonance. So let's do some practice problems. Predict the products and the direction of the equilibrium. Go ahead and pause and try these yourself and think about it, and then we'll come back and do them together. Okay, so let's work on these together. Remember that sodium hydroxide is sodium plus and hydroxide minus. So we have the hydroxide base, and we can deprotonate our phenol to give phenoxide plus water and plus sodium, if you really want to be specific here. Sodium is now the counter ion to phenoxide. So which way does this equilibrium lie? Well, the pKa of the proton on phenol is 9.89. The pKa of the proton in water is 15.7. Which side has the weaker acid? It's the product side. So we are going to favor the products. Now let's look at the bottom one. We have hexanol. That's 1 hexanol. The pKa of this proton is around 18. If we take our hydroxide and deprotonate it, we end up with an oxygen with a negative charge, counter ion sodium plus water. The pKa of the proton on water is again 15.7. So which side does the equilibrium lie? Which way does it favor? So this time it's going to be the reactants. The reactants has the weaker acid. So this reaction would not really go forward, but it would be at equilibrium because the pKa's are fairly close together. So let's take a look at organic compounds as bases. So if we have an alcohol reacting with HA, which we'll call HA just a generic strong acid, an alcohol is very, very similar to water, and its reaction with a strong acid is going to be very similar to water. It's going to pick up the proton, break the bond between the proton and the A, whatever that is, and now you have an oxonium ion, which is equivalent to the hydronium ion formed with water and acid. And you would have the conjugate base, A-. If you have an ether, all we've done is swapped out this hydrogen for this carbon. We're going to end up doing something really similar. So again, just protonating the oxygen and creating the conjugate base. And you can do the same thing with ketones. You can actually protonate a ketone and then this has a cool resonance form that ends up being the foundation of a lot of chemistry in OChem 2. And interestingly enough, you can also protonate an alkene. Even though there's no obvious base in the alkene, these pi electrons are quite reactive. And so you can actually pick up a proton and break the bond between the proton and its future conjugate base. Your carbon framework would stay the same. The proton would end up on one of these carbons, and you'd end up with a carbocation on the other carbon, plus A-. And this is the foundation of the chemistry that you learn in chapter 6 or 7. No, 7 or 8, sorry. Okay, last topic here is the solubilization of organic compounds through salt formation. So a salt is a water-soluble ionic compound, an electrolyte. And for example, you can take an insoluble solid such as benzoic acid and react it with sodium hydroxide. And what this is going to do is allow the hydroxide to remove this proton so that you end up with benzoate, the conjugate base, with the counter ion sodium. So it's now sodium benzoate plus water. And having this ionic species here is going to make this much more water soluble. You can also do this with amines. This compound below is 1,6-hexane diamine. This is something that I actually used a lot in my graduate research, and I often had to get it to go into an aqueous solution. And the way to do that was actually to dissolve the 1,6-hexane diamine into an ether, such as diethyl ether or THF, and add in hydrochloric acid as a concentrated gas, which was really cool. It was just like creating a bubbler of acid into this compound, and the diamine was soluble in the ether and the salt was not. So the way this works is each amine picks up a proton from hydrochloric acid. And that makes it positively charged. And you'll have the counter ion. And you'll do this, it'll happen on both sides, and that ends up making it water soluble, which is really cool.